All right, everyone. Today we're looking at section 2.5, limits that are infinite. So to start off, I wanted to have us graph a piecewise function that has some of the properties that we look for to know if a limit will be infinite. So for this piecewise, we're starting off with x less than or equal to positive 1, and we have the graph 3 over x squared times x plus 2. So first thing, I want to calculate the y value when x is equal to 1, because that's where the rules are going to switch. So if I substitute 1 to the top rule, I get 3 over 1 squared times 1 plus 2, so 3 over 3, which is 1. So 1, 1 is that point. And other than that, we have a couple of other points or things about this graph that we can look at. So first off, because I have two expressions that involve x in my denominator, I know that we're going to end up with some vertical asymptotes. Because remember when we talked about math no-nos in the last section, one of them was that we can't divide by 0. So I know that we would end up dividing by 0 if x were equal to 0. So we're going to draw a vertical asymptote there. And when x is negative 2, we're going to draw another vertical asymptote there. And another thing, if you remember from your algebra or pre-calculus classes, because the degree in the denominator is larger than the degree in the numerator, this piece of the function is going to have a horizontal asymptote on the y-axis, or the x-axis. Yeah. All right, and because we already calculated this point when x is 1, we know that for that piece of it, the y value is going to be higher than the asymptote. Now we can use the multiplicities, that's to say the powers of each of these factors in the denominator, to figure out what the behavior is around the asymptote. So when x is 0, we have an exponent of 2, that's an even number, so they will both be approaching the same infinity. When x is exactly equal to negative 1, just for fun, let's see what we get. We get 3 over 1 times 1, so we get negative 1, 3. And we'll end up getting that kind of behavior on the right side of the asymptote. Since x plus 2 has an odd exponent, right, the exponent's 1, we know that the other side of this asymptote, y, will be approaching negative infinity. And for fun, let's see what the graph, what the y-coordinate is when x is negative 3. So you'd get 3 divided by 9 times negative 1. So that would be negative 1/3, somewhere between 0 and negative 1. And then typically we also want to look for where the y-coordinate would be equal to the horizontal asymptote for rational functions, because they can cross the horizontal asymptote. That's the thing that can happen. But if I were to set that top rule equal to 0, I try to solve that equation, I end up getting 3 equals 0, which has no solutions. So we know that in the long run, the y-coordinate will be approaching but never reach 0. Now if I look at the other one, the bottom rule, I notice that I have x squared minus 16 over x minus 4, which is something that can be simplified. So if I were to factor that numerator, I would get x plus 4, x minus 4. That's the difference of two squares. So then what I notice is that I have a factor of x minus 4 in the numerator and in the denominator. So these would divide, they would leave behind a 1, and I would essentially find that the graph of that bottom roll is a line. It looks exactly like x plus 4, except when x is equal to 4. When x is equal to 4, well, remember in our discussion last time, we said that we wouldn't be able to use that because we would get 0 over 0. So x plus 4, if I substitute 4 into that, I get 8. So if I go over 4, I can go up 8, which is going to be high up. We'll just let that be 8. I get a line. Other thing I want to check for sure is the y-coordinate when x is equal to 1, right? Because we want to see if it lines up with the y-coordinate from the top roll. So when x is equal to 1, 1 plus 4 would give me 5. So, yeah. So I'd go over 1, and then up 1, 2, 3, 4, 5. Which, since I scaled the 8, that's going to mess it up a little bit, but yeah. So then we end up getting a straight line that goes through there and a straight line that has a hole. So it's actually going to be a tad bit steeper, but I couldn't reach 8, so yeah. But now that we have a graph, we can go through and look at some limits. So first set, let's look at the limits as x is approaching -2, from the left, from the right, and overall. So as x approaches -2, remember that's our vertical asymptote over here. As x approaches -2 from the left side, I notice that the y values are getting more and more negative. So we would say that this limit is -infinity. And like at the end of last video, I mentioned you could also say it does not exist, -infinity. But for the purposes of this, we want to specify that it is indeed going to -infinity. Okay, so then next we look at the limit as x approaches -2 from the right side. And I notice that this is going the opposite direction, right? So as x gets closer to -2 from the right side, from the positive side, the y-coordinate is approaching +infinity. It's getting more and more positive. Now, so even though both of these limits one-sided are infinite, right, we still need to think about, are the y values approaching the same thing from both sides? They're not. So for the overall limit as x approaches -2, I would say that limit does not exist. Now, if we look at the limit as x approaches 0, we see that kind of the opposite thing is happening. Because as x approaches 0 from the left-hand side, y is getting more and more positive. As x approaches 0 from the right-hand side, y is getting more and more positive. So in that case, since both of the limits are approaching +infinity, that's what we write. But note, they had to be the same sign infinity for me to say that. If they had approached different infinities, like one approached -infinity, the other approached positive, I would have had to say D and E like I did with the limit as x approaches -2. Now, looking at the limit as x approaches +1, well, we can tell, oh, that should be an open circle, not a filled in dot. Whoops. All right, but we can tell just by looking at that that's going to be we're going to say the limit does not exist for that one, because as x approaches 1 from the left, y is approaching 1. As x approaches 1 from the right, y is approaching 5. Not the same number, so the limit does not exist. Now, other one we've seen on a graph before, limit as x approaches 4 of y. So as x approaches 4 from the left, y is approaching 8. as x approaches 4 from the right, y is also approaching 8. Same value, so the limit exists and is equal to 8. And so at this point we've kind of seen that having vertical asymptotes, meaning factors that don't divide out when we simplify in the denominator specifically, result in limits that are infinite. Some other types of functions that have vertical asymptotes that we should be aware of are logarithms, tangents and cotangents, and secants and cosecants. So with logarithms, as x approaches some value that we'll call a from the right, the limit of, it could be a natural log, it could be any log, any base of x minus a is equal to negative infinity. All right, and this goes back to what we discussed in the last video about the graph of a logarithm. If I have a logarithm that's shifted a units to the right, I'll have a vertical asymptote at x equals a, and then depending on whether x takes on a positive or a negative coefficient, that tells me if my graph will be on the left or the right of the asymptote. Here the coefficient of x is positive, so we're going to go to the right and make our bendy straw. So you can see as x approaches a from the right hand side, the y values are getting more and more negative, which is why that limit is negative infinity. With tangents and cotangents, remember from your unit circle, tangent of theta is undefined when theta is pi over 2. So for tangent, you have to remember what the graph looks like. At basically odd multiples of pi over 2, they're vertical asymptotes. And it goes on in both directions. So you'll notice that as x approaches pi over 2, or any of its odd multiples from the left-hand side, the y is approaching positive infinity. And from the right-hand side, the y is approaching negative infinity. And that's a property with tangent graphs that we should be aware of. We actually see a very similar thing with secant graphs. Yep. Actually, we see the exact same thing with secant graphs. With cotangent, though, and cosecant, right, there's a different value that we have to be concerned about, and the behavior is a little different. So when x is 0, we have this vertical asymptote, and then we have it again at multiples of pi. So with cotangent, the graph looks like this. So it's almost like a shifted and reflected tangent graph. And then it continues in both directions. So here we would see that the limit is x approaches pi from the left-hand side is negative infinity, and as x approaches pi from the right-hand side, that limit would be positive infinity. So with secant, you'll actually see the same, or not secant, cosecant, you'll actually see the same pattern. It's just they have a different shape to their graphs. So instead of these squigglies, they actually have little cups, like boom, boom, boom. Yep. That about sums up my demeanor right now. But yeah, so you can see that they have kind of a similar thing going on. So it's important for you to know these different types of functions that naturally are going to have asymptotes. And the way that I want you to think about them when you encounter them in the wild is if I plug in a number that makes the argument of a log closer to 0, then that log is approaching, the value of that log overall is approaching negative infinity. And of course, you also have to think about transformations to it. Like if it were a negative log, you would be subtracting a really big negative number. So you would be adding a really big positive number, because subtracting a negative is adding. But yeah, definitely know which functions have asymptotes like this. These are the ones you need to know. And with that, we'll look at some examples of just evaluating some limits. So first up, we've got the limit as x approaches 2 from the right of 1 over x minus 2. So here's the idea with this one. If I plug in numbers that are slightly greater than 2, I'm getting a denominator that is positive, right? So 1 divided by a positive number gives me a positive number. 1 divided by a very, very, very small number gives me a very, very, very big number, right? Because if you think about it, if I were to hold the numerator constant and just make the denominator smaller and smaller, the value of a fraction would get larger and larger. Like if I were to take a pie and cut it into smaller and smaller pieces, I'd be able to get more and more pieces of pie. All right, but anyway, so we get a really big positive number that translates to positive infinity. Now if I look at the second one, this is something that I can factor in the denominator. So this is equivalent to the limit as x approaches 1 of x minus 1 over x minus 1 times x plus, or not x plus, x minus 3. So that x minus 1 factor is going to divide, it's going to leave behind a 1 in the numerator. And we get the limit as x approaches 1 of 1 over x minus 3. So thing I want to note here is that because there was a factor that divided out, this results in a removable discontinuity. All right, and what that means on the graph is that the graph behaves exactly like what's left behind after I simplify, except at the point where there's a removable discontinuity. So if I were to ask you to find f of 1, then your answer would be undefined. But because we don't care about what's happening at 1, we only care about what's happening nearby, we can plug the number 1 in and we'll see what the y values are approaching. So if I plug 1 in for x, I get 1 over negative 2, which means that my limit is negative 1/2. All right, and then one that involves a logarithm. So remember what I said about how to think about those other kinds of asymptotes. If I plug in a number that is just slightly less than 1, like 0.9 or 0.99. 1 minus 0.9 gives me 0.1. 1 minus 0.99 gives me 0.01, etc., etc. So I notice that the inside of my logarithm is getting closer to 0. And remember, if the inside of the log is getting closer to 0, that means the log all around is getting a value that's closer, that's more and more and more and more negative. But if I look at my numerator is just x, right? So the numerator is just getting really close to 1. The denominator is getting really big and really negative. So we would end up having a negative number, right? A negative number that's getting close to something. Well, let's think about what. If I take a number like 1 that's constant, and I divide it by something that's really, really big, what does that give me? 0. Going back to our pie analogy, that would be like if I were to cut that pie into super, super small slices, each slice would get smaller and smaller to the point where you're like, you're not even giving me any pie, what's up? So 1 over a very large negative number approaches 0 as that number gets more and more large. All right, and then last one, we have the limit as x approaches 1 from the right of some trig stuff. So first off, sine. Sine is defined everywhere, so there's nothing wrong with me just substituting the 1 in for that x. The issue happens when we get to that tangent. So I know that this limit for the sine is going to be sine of pi over 2, which is 1. All right, but with tangent, the argument, the inside of tangent, is approaching pi over 2. And we just saw in the graph that when that happens, you have one side that's approaching negative infinity and one side that's approaching positive infinity. Well, if we visualize the graph for tangent, remember we had our squigglies and we had these asymptotes. And it goes on in both directions. So as x approaches 1 from the right, the y value gets more and more negative. So we would say that tangent of that value is approaching negative infinity. So next thing to consider, if I have a number that's basically 1, and I'm subtracting something super gargantuan, gigantic big, well, what is that whole overall thing going to be? It is also going to be super negative, super big. So that limit would be negative infinity. So long story short, get to know your asymptotes with logs, tangents, secants, all that. And when you have just regular rational functions, start by looking to see if you can factor anything out. If you can, then a lot of times that results in a removable discontinuity. If you can't, then just think about what's happening within the expression. Like in that first example, the denominator was becoming a very, very small positive number. Dividing 1 by a small positive number gives me a very big positive number. All right, so that's kind of the reasoning, the logic that you could use to evaluate some of these limits when you don't have a graph available. And yeah, have fun.